Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the mathematics series, I actually thought I needed to really upload this on time, but then I realized this stuff isn't for people so it shouldn't matter too much, right? Right. At least you'll have it in time for paper too. Okay, so today's topic is discrete random variables, which is part of the statistics. So that's why it's not very needed for paper one, but more for paper two. Anyways, so I'll just go through the points quickly, and just if there's any need to mention about the GC, I'll just mention it. Okay, so this is like a little foray into the main part of the statistics, you know statistics in the sense, because instead of looking at normal distribution first, you're looking at binomial distribution, which is a bit more idealistic, or like not idealistic, may not be that realistic in a way. But anyway, let's first talk about what exactly discrete random variables are and some other terms along with it. Okay, so you know what is a variable, right? In an experiment, it's like what you call a factor, like whatever affects the experiment or whatever is affected by another variable. So in this scenario, these variables are discrete and random because if you think about it in a binomial distribution, you can have it repeating many times, but every time the thing is reset. So like in the previous video when I talked about the replacing the red back in, it is kind of like that. Like you always start from a fresh slate every time you take a turn. So that's why it is in a way independent of each other, and it doesn't like influence other variables in the future. And it's random because, well, at the end of the day, the world is is powered by randomness, by chaotic stuff, and that's why it has to be random. But in a way, you can never really have a truly random, like 100% random experiment, because there are many things that affect it in a way. Even if you say you have a fair dice, which is obviously unrealistic, even the real world so-called fair die will not be entirely fair, like 100%. Maybe it's like 90+%, but not 100%. There could be like some sediment that settled on one side and then made that side heavier. That could very well happen. But anyway, let's not go too deep into that kind of stuff. Let's just focus on the idealistic situation. Okay, so so it's discrete because it's like it happens individually, and it's random because you can't really predict it, like precisely because it's so-called independent. You can only have a certain probability. You don't really know if it will really happen or not. Okay, so probability distribution. As I mentioned in the previous video, one way of actually representing it is with a table. So if you have the probability of something happening in the first row, and then in the second row you can write the thing that happens in the first row, and then the probability in the second row. Yeah, so that's how you would do a probability distribution. So like for example, if you had the scenario of using a like two dice, and then you roll them and you get a certain number out of it, you can get a probability of each pair of numbers through the use of a probability table. And from there you can, if you want to look at a sum or anything else for that matter, you can count them up, and then you can find the probability of getting that sum. So they might ask you a question like this, but that is a pretty straightforward question, so I don't know whether they will actually be bothered to ask this, because it takes a lot of time to write the table and everything. It's not worth it. Anyways, okay, so the expectation is kind of like what you expect the most out of the experiment. So like for example, if you have a higher probability of getting red than blue, then you would expect to get red this many times out of whatever number of times that you take it out. So like for example, if you have 9 red and 4 blue, and you decide to reset the experiment every time, and you do a taking out 13 times, sorry, yeah, 13 times, you would expect to get red 9 times. But it's not likely that you will get red 9 times precisely because you reset the thing every time. So you can keep getting blue for that matter. It's totally possible. But the expectation is what you would usually expect. And the variance. Okay, so the variance is kind of like the spread, like how spread out the data is, like how spread out the probabilities are in the sense. So if the peak is like very centered in, like if the middle part is very has a high probability, then the variance might be, like how do I put it, the variance might be lesser. But if it's very spread out, then the variance might be higher. But I'm not sure if I'm saying this correctly, so don't take my word for that. But you get the idea. It's something to do with how spread out the data is. Okay, so let's move on. So why do we look at binomial distribution? Because we can just always come up with some idealistic situation which fulfills bunch of conditions, and say, okay, we can apply binomial distribution to this. So what do you mean by binomial distribution? You know that there's a bi in it, which means 2. So one of the conditions has to do with the fact that you can only have 2 different outcomes, either yes or no. Like for example, like one event or the opposite of the event. You cannot have any other outcome happening. So in our scenario, for example, if we have red and blue, you can say it's either red or not red, which should be blue. But if you have red, blue, and green, you must define it as, if you want to look at red specifically, then you can say it's red or not red. But not red will include blue or green. So you must take that into consideration when you're doing your binomial distribution. But the thing is, with binomial distribution, you can actually do your little probability trees, and you can always put it into 2 branches, no matter what. And it's quite easy to calculate from looking at the tree. But yeah, that's just how it works. And the other condition is about the independence. I'm not sure about the exact phrasing, but like the events must be independent to one another in a way. Okay, so yeah, so how do you use the binomial distribution? Well, you would kind of you'd write the b bracket np. So n is the number of times you do the thing, and p is the probability of getting a certain event based on what event you specify in a sense. So like for example, if you have the probability of x happening, and you approximate it to the binomial distribution, the probability would be referring to the probability of x happening in a sense. Yeah. As you can see, it's a bit idealistic because it's not really how the real world may always work. You may not always have your experiment resetted every time you do it, and it may not always be the same conditions when you do one experiment after another. That's why you can only use this in your maths paper, or in very specific scenarios in the real world. If you are willing to really idealize that situation, you can do that, but you must also realize that it may not be the best model. But in the questions, yeah, you can just use that and state the 2 conditions and go ahead. That's your job. Don't worry about it too much. Okay, so how do you use, what does it mean? What is the meaning of binomial distribution? You do realize that we have already covered the binomial expansion in a previous chapter, so you just need to use that and you get your answer kind of. So like for example, if you think about it in a very rational way, yeah, like getting red this many times versus getting blue this many times, you can, if you were to replace it every time that you do the experiment, you can also calculate it that way. Or if, and so on and so forth. But anyway, the idea of binomial distribution calculations is, for example, you have your probability table, and then from there you can say this thing times that probability, and then this many thing times that probability, and so on and so forth. Yeah, so yeah, well, you would usually be asked to calculate events happening in succession. So like, for example, you say you get red 2 times out of 5. So instead of drawing a tree for the entire thing, you can use this to calculate your probability. So you can actually use a calculator, your GC or even your scientific calculator, if you know how to use it, and type this in and you'll get your answer, kind of. If you want to do this manually, I think it's possible as well if it's a small number. But if it's something like 25, then I don't think you want to be doing this manually. You should use your calculator to calculate it. So for example, if you were to use the scenario of 2 red out of 5 times, then if you look at it manually, you would know that the red probability is always 9 over 13. So you would have 9 over 13 twice, and then 1 minus 9 over 13 3 times. And that's how you get your answer. But if you were to do it, I mean, you can do it for 25 things as well if it's always replaced every time. And you can do that in your calculator as well. So it shouldn't be too hard to calculate the binomial distribution. It's more of the normal one which you can't really calculate on your own. You need a calculator for that. Okay, so you just need to just know that that's how it works in a way. So the final point is about mean and variance of binomial distribution. So in a binomial distribution, what would be the average thing? What is the mean of it? If you think about it, it would be the probability, right? If you can look at the probability to figure out what is the mean. So let's say if your event X has a 40% chance of happening, and you try to do this 10 times, what is the mean number of X's that you will get? 4, of course, because you times X by you times 10 by 40% and you'll get 4. So you're going to be expecting to get 4 X's for every 10 tries that you do. So likewise, if you think about it in that way, the mean would just be n times p. And for the variance, it is actually n times p times 1 minus p. As you don't actually need to know the proof for this, but there is a proof. So if you want the proof, I can show it to you later on, but I don't want to write it down because yeah, I'm not that good at statistics, so I can tell all these things, but I do not know how to do the proof that well. I guess the reason is because if you think about it, you have the probability of the thing happening. So let's say in our example you have 4, then you times it by 60%, and you would get 4 times 60% would be 2.4, and that is your variance. So the difference between the middle point and the average and the next standard deviation is about 2.4 again, I think, I don't know. So it shows how spread out it is. And I think the probability of the event not happening affects the variance in that sense. So if your probability is lower, then the probability of it not happening is higher, right? So the variance will end up being a bit more closer to each other compared to when the probability of your event happening is very high. Wait, what? Okay, I'm confused. No, if your probability is pushed all the way to that one side, then your variance will be a bit more closer compared to the average, in the sense. I do not know what I'm saying, so yeah, it's okay, you don't need to know the proof. Just know how to do the mean and the variance. Okay, so yeah, I think that's about it. If you really want to know about the proof, then I will try to read it up and then show it to you separately. But for now, I hope this is actually a really short video compared to what I usually do. It's only like 15 minutes long. Great. So with that, once again, good luck for your exams, not just your maths, but everything. And if you found this video useful, please press the like and subscribe. With that, I would like to say thank you and bye.